Hello, and welcome back to our Data Structures and Algorithms series. In this video, I'm going to teach you about an important concept in computer science and software engineering, the Big O notation. In order to be able to create applications that offer great user experiences and applications that can scale, you must understand how to analyze and optimize your algorithms. That is where the Big O notation comes in. So in this video, by the end of it, you should be able to understand what the Big O notation is. You should be able to understand the different types of Big O complexities. We are also going to see how to apply Big O to practical scenarios and how to analyze the algorithms for time and space efficiency. So what is Big O notation? Big O notation is actually a way to describe the efficiency of an algorithm. Now, that is actually how the performance scales as the size of the input increases. Now, we are going to be dealing with different algorithms, and these algorithms have different capabilities in terms of how they perform and use computational resources. These resources are mainly the CPU, time, and the memory. Now here, you must get one thing clearly about the Big O notation, that really we are looking at how your application is performing when the size of the input grows. Now, for example, it might be quicker to send a letter via email rather than to post it. But that's only in situations where the file you want to send over email are small file sizes. For example, if you wanted to send a 1 terabyte message over email, depending on your network speed, it might be a daunting task that might take a very long time, compared, for example, to posting that particular maybe flash drive that has that file, and that maybe is going to be carried over just in hours to its destination. So we're not really looking at the speed, how fast your algorithm executes, but really how well it will be able to handle the large inputs. When the inputs become very large, then how is it going to perform? That is what Big O notation really gives us. Now, if you can remember, a computer algorithm is actually a set of logical steps, logical steps that will enable a computer to solve a particular problem. What is important to mention here is that there can be several different algorithms for solving the same problem. For example, we looked at finding the factorial of a number using recursion, right? But we can also calculate the factorial of a number using an iterative solution, iterative algorithm. So as a computer scientist, there is always several options, and each one of them has a certain advantage over the other. For example, when you talked about solving using recursion factorial, we know that the space, recursion uses more space because every recursive call is added to the call stack. On the other hand, iterative solutions do not need to use an extra space for that. On the other hand, maybe, and I'm just saying maybe, maybe the recursive solution might perform faster than the iterative solution. That is not entirely true, but I'm just saying maybe. So you'll always need to know how your algorithm will perform And what then you need to put into consideration, is the space more important than the time, or vice versa? So you'll end up choosing an algorithm depending on those two things. For example, we know that phones, for example, come with limited memory. So if you're building an application that is going to run on a phone, then you might go for the iterative solution, which is more space conscious compared to, for example, the recursive solution. So what I'm trying to make very clear here is the fact that you are now going to use big O notation to analyze your code, your algorithms, and be able to choose which one is best depending on the scenario. So again, big O notation is not about measuring the speed of your application. That is how fast your application runs. No, 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 no. It's actually measuring the amount of work. You remember the steps that the algorithm is going to take from getting the input to producing an output. So the amount of work that the algorithm is going to do as the input increases, as the size of the input increases. So that is what big O notation is about. Now, big O notation, when we are analyzing algorithms, we talk of algorithm complexities. So big O notation actually helps us to analyze the algorithm complexities. And we have two types of algorithm complexities. We have what we call the time complexity, and we have the space complexity. So time complexity describes how long an algorithm takes to run as the size of the input increases. So here is actually a graph that is showing us different graphs for different time complexities. You can see that on the y-axis, here, we have the CPU operations, which is actually the time that is going to take the CPU to complete that particular task. And on the x-axis, we have the input size. So as the input increases, how does the time the CPU takes to solve that particular challenge, how does it behave? So we have what we call O of 1 here, O of log n, O of n, which we are going to understand shortly. But as you can see with the colors, algorithms like these ones, where as the input size increases, then the time really shoots up very fast. They are terrible algorithms. And the best, of course, is what we are seeing down here, this one, O of 1, because no matter the size of the input, then it's going to take the same amount of time to solve that particular problem. So that is time complexity. Then we have space complexity. And as you might have guessed, here on this graph, on the y-axis, then we have the space requirement. How much space do we need? Then n is the size of the input. So the number of inputs that you're putting there. So as it grows, how does the memory requirement also correspond? So as you can see, we have the same representations, O of 1, O of log n, O of n, etc. It's just the same. So this is what we call the big O notation. Now, the tech bros, as they call them, love Audi. Now this is an Audi Q7, and this Audi will perform differently in terms of fuel consumption depending on different scenarios. For example, on the worst case, that is on traffic jam, it's going to consume 8 liters per 100 kilometers. On the other hand, if you have a mixed case where you have traffic jam and you have highway, then it's going to consume maybe 5 liters per 100 kilometers. And on the average case, if we have just the highway, then it's going to consume between 3 to 5 liters. So why why is this important? Why is this important? This is important because it enables you to know how much you're going to be spending. Because I know you guys are going to buy an Audi at some point. How much you're going to be spending, for example, on fuel in a month. So we've seen that the worst case is 8 liters. So most of the time you want to plan with the worst case if you want to plan your money. So you want to multiply 8 liters by the number of kilometers maybe you normally take times the price of fuel, so that you can save that money and budget it for fuel for your car. Okay, now these same considerations are looked into when we are looking into algorithm runtime notations. So we normally look at the best case, that is at the very best, how much time will your algorithm take to give us a solution to the problem. Then we also have the average case and the worst case. And of course, this is in relation to either the time or the memory. And on this x-axis is as the size of the input really grows. Now, in order to represent each of these scenarios, we normally have what we call the big O. So we have the big O notation. So the big O notation really normally gives us what we call the worst case scenario. Then we have big theta written as that. So big theta normally gives us the average case scenario, and we have the big omega, which normally gives us the best case. At the very best, how is your algorithm going to perform? So those are the three runtime notations that we use: big O, big theta, and big omega. Now, when we are analyzing and optimizing algorithms, we are most concerned about the worst case. That is, at the very worst, if 1 million people are accessing the system, how is our algorithm going to perform at the very worst case scenario? So because of this, normally we only discuss and are concerned about the big O notation and not about the big theta and big omega. We are not concerned about the best case. We just want to optimize for the worst case. Okay. Now here is a list of the big O notations. Now the first notation is called constant time. And the notation name is O of 1. So you might ask, what does this really mean? So let me just give you an example. So for example, let's say we have an array that has several numbers in it. So we have an integer array like that one. Okay, so if we want, for example, to access any item in this array, we will simply do the array name, then we put the index of that particular position that we want to read. So for example, if we want to print out 4, then we will do array 0. So it will take some time. So let's now go to this graph. So it will take some time. Let's say it has taken this time. So I'm just plotting an X here. Now, if we do access another index, for example, this index to print 7, again, it will take some time. If we want to access, for example, 8, we'll just put the index there, and it will take some time. So it doesn't really matter how big this array is. even if it has 1,000,000 items, if we put the index of 1,000,000, it's going to take the same time to read that particular element in that array. So that is how we get this constant time graph. That's how we get this constant time graph. So really, what this means is that the time, because y-axis is time, the time it takes to read the values in an array, a single value in an array. Let's say, for example, it took 0.5 seconds. In all the instances, it took 0.5, 0.6 or something. So on average, let's say it's 0.5. Now, what happens is that this constant time is normally rounded up to a 1. So that's why we have O of 1. Okay, so O of 1 is actually called big O of 1, that constant time. That's why it's called big O notation. It's normally big O of 1 or big O of log n, etc., etc. Now let's look at another example. For example, how do we come up with a linear time? So for the linear time, it's called O of n. So how do we get O of n? How do we get this O of n? And I know this is not very easy to understand the first time, and big O notation is actually a mathematical concept, and there is a way they come up with each of these formulas through a rigorous mathematical process. So here I'm just giving a rough explanation, but I encourage you to read further, watch other videos on this so that you can be able to understand it better. So for example, let's use the same example of our array. So far, our array has 1, 2, 3, 4, 5 items. So if we wanted to print these 5 items, then our array is going to take some, our algorithm is going to take some time to read those 5 items. Now, if we increase the size of the items in the array from 5, let's say, to 10, of course, it's going to take some more time to read it. If we increase it to 100, it's going to take some more time. If we take it to 1,000,000, it's going to take some more time. So if we draw that particular graph, then it's going to be a linear graph. Now, if you can remember some little mathematics, this particular kind of graph normally has that equation, a representation of this equation. Y is equals to mx plus c. But remember, for us, we do not have y, so our y-axis is actually t. So our time is, so we're having some constant, let's say m. Remember, m is just a constant. Then our x is actually n, which is the number of items, then plus c. Now the rule, we have 2 rules in coming up with a big O of something. The first rule is that you drop any constants. So here we are going to drop this constant. We have the constant c, so we are going to drop it. Then we also have a constant m, so we are going to also drop that constant m. And therefore our t now is going to be, our time is going to be big O of whatever is remaining, which is n. So that is how we get big O of n. And all these other big O notations have a mathematical way of how they arrive from the equation to that. So I mentioned something and it wasn't very clear. There are 2 rules when you've come up with this equation. The first rule is dropping non-dominant, non-dominant parts. So any equation that is not growing so fast, like C is just alone here, so we're going to drop it. Then we're going to remain with Mn. Then after dropping the non-dominant, then we drop the constants. Any constant is dropped. So if we do that with this equation, then we begin by dropping C, then we are left with Mn, and M is also a constant, so we drop it again. So we are left with just N alone, and that now gives us our big O notation. T is equals to O of N, where N is the number of inputs, the size of the array, for example. Okay. Okay, so in this table, we're just giving you another example so that you can just see that the big O notation name is this, whatever is in this column, like big O of 1, big O of log n, big O of n, etc, etc. Then it also has a name. So I might ask you, for example, to analyze a code and tell whether its runtime is constant time. So constant time means big O of 1, or logarithmic time, or linear time, or quadratic time, etc, etc. So we're going to be looking at different examples of scenarios where the runtime is either constant or logarithmic or linear in a bit. Now, as software engineers, we should always strive to keep our algorithms to run in either this light green or green, good or excellent. So that is, our algorithms will be doing so well if they're running on O of 1 or O of log n. So those are the best. Now, when your algorithm begins running at O of n, it means that as the size of input grows, the time it takes also grows quite fast, and that's not so good. So that's just fair. Then when you get to the orange bit here, it's not really nice, and the pink area here, things are really bad. So that's why we normally look into the algorithm and try to optimize it to bring it down to or big O of 1 or big O of log n. Okay, so if you look at this, you can just pause the video and give it a try. What do you think is the correct answer here? Which big O notation represents the fastest growing complexity? So which one is the worst? Which one will grow very fast? Is it O of 1, n, or n of log n, or n squared, or log n? So I can just take you back to the graph again. You have a look at that. Okay. Okay, so yes, the answer here is C. Okay, so I hope you understand why. Okay, so this is what I was telling you. We will be calculating the runtime of your algorithms by analyzing each line of code. So normally, these are the standard runtime complexities for the different operations. So for example, when you declare a variable or assign it to a value, then that is what we call assignment. It's normally just an O of 1 operation. conditional statements, if, else, O of 1. When you do a return statement in a function, normally an O of 1. Now, if you have one loop that has not been nested, of course, the loop will run for until the condition is met. So it will run n number of times. So that one normally gives us an O of n time complexity if you meet a loop. Now, if a loop has been nested in another loop, for example, we are going to look at an example shortly. So if a loop is nested inside another loop, then normally the time complexity is O of n squared, because it's n times n. So that gives us n squared. If there are 3 loops, then you've guessed it right. It will be n cubed. Now, if you have a problem where the data set is halved at each step, then that gives us an O of big O of log n time complexity. For example, in binary search, we are searching through a sorted array. So normally, because it's a sorted array, if, for example, we are looking for, let's say, we have number 9 here, then on these sides, we have number 10. And this is beginning here at, for example, 1. So in binary search, we normally begin at the middle of the array and we check. So for example, we are searching for the number, we are searching, for example, for the number 8. So we will come at the middle here and check, is 10 greater than or less than 8? So if it's less than 8, then we take the half below number 10, like that. Then again, we come to the half here. Then we check whatever is in the middle here. Let's say it's number 5. So we check, is 5 greater than or less than 8? So because 8 is greater than 5, then we take from number 6, we take the next half, like that. Then we again, so now, of course, now here we have number 7 and we have number 8. So again, we check in the middle here. So you see, we've halved the problem. We've halved the problem. So we've not just searched like a linear search. In a linear search, we visit each item one by one. Okay, then at the very last, again, it's a tip. So when you have multiple statements in your algorithm, we simply sum up the runtime complexities of each line. Then we drop any constants and we drop any non-dominant terms, any terms that are not growing very fast. We simply ignore them. And there's a reason why we do that. Again, I want to encourage you to read more about that. Okay, so let's have an example here. So how do we analyze the time complexity of this code? So let's begin. So here, let's just begin from the top here. So here we are defining a function. So this is just like a declaration. So this will be an O of 1. So that will be an O of 1. Then here is an if statement. Remember, we said an if statement is just an O of 1. So O of 1. Then we have a return statement. Again, this one is O of 1. O of 1. The else here is also going to be O of 1. O of 1. Return statement here is also O of 1. O of 1. That. Then we have a declaration of an array here. So this one is also O of 1. So O of 1. And finally, we are printing. So this one is also O of 1. So all these statements are O of 1. So what we do is we are supposed to add all of them. we're supposed to add all of them. Now, if we add all of them, we are going to get the overall for this is going to be because of the two rules. So let me just do it. So we have O of 1 plus O of 1 plus O of 1, like that. So this one is going to give us, let's say, O of, let's even say 5, for example, like that. So you see, normally when we have an O of a number, remember this is just a constant time, because it simply means that it's going to take that same amount of time all the time you run this code. So this can be written as that, O of 1. So the time complexity for this code is actually O of 1, a constant time. So let's look at another example so that we can get even a better understanding of this. So here we have a function to calculate the sum of items in an array. So that is what we have. So let's begin maybe here where we are declaring. So the time complexity for this one will be O of 1 for declaring the array, and also for calling and printing here, it should be O of 1. Here, this is O of 1. Declaring the total there is also O of 1. Then here we have a loop. So remember, anytime we see a loop, because it's going to loop n number of times, so that is going to be O of n, depending on the size of the array, the number of items in the array. So that's O of n. This one here is O of 1. And the return statement here is also O of 1. So what you do again is you add all of them. So let me just do it. So we will do from the very top O of 1 plus O of 1 plus O of n plus O of 1 plus O of 1 plus O of 1, and lastly plus O of 1, like that. Okay, so once we have this, we are supposed to drop any non-dominant terms and also drop the constants. So here we have the constant times, which we can simply drop. So we can drop all this so that we just remain with O of n. And therefore, the runtime complexity for this particular code, the overall runtime complexity is actually O of n. So normally, we drop the non-dominant terms because they are terms that do not grow, and therefore, they cannot impact the overall runtime of the program as the input increases. They do not impact. But any term that grows, like this n, then is what we really care about. Because if the size of this array is 1,000,000, then n indeed is going to take a lot of time. But when the size is 1,000,000, the total here is still going to be O of 1. This one is still going to be just the same. It's going to take the same amount of time, constant time. Okay, then we can look at another example. Now, in this example, we just want to look at when do we add and when do we multiply. When do we add and when do we multiply when we are calculating the time complexities of a program. So anytime you're having a nested loop, so that's just what I want to show you. Anytime you're having a nested loop, like here, we have a loop inside another loop. That's a nested loop. So that means that the time complexity here is O of n, and the time complexity here is also O of n. Sorry. Like that. So when you have this, because it's a nested loop, each one of them is iterating in the array. This is when you multiply. So this is going to be O of n times O of n, and that's how you're going to get O of n squared. On the other hand, we've been adding all through. We've been adding those examples that we've looked at. So for example, if you have one for loop and it's following another for loop, then we are going to add. So this for loop here is going to give us an O of n. So I just want to show you that. So this one is going to give us O of n. By now, of course, we are almost ignoring the O of ones because we know after all, we are going to drop them. So we have O of n and we have O of n squared. So this is going to be an addition. So we have O of big O of n plus big O of n squared, like that. So remember, so what we're actually doing right now is calculating the time complexity for this code. I've just ignored all the O of ones, but we have O of n and we have O of n squared. Now remember the rule. The rule is that we should drop any non-dominant term. That is any term that is, we are supposed to keep only the fastest growing term. So you see, here we have O of n and we have O of n squared. So which term among these two is going to grow at a higher rate? Of course, you've guessed it right. It's this one. So we are going to drop this one because it's non-dominant. So that is what that means. And therefore, the overall time complexity for this particular code is going to be O, big O of n squared. So that is how we arrive at this particular results, time complexity. Okay. Okay, so as we wind up, let's also look into space complexity. So time complexity is important, space complexity is equally important. So just like we did with time complexity, with space complexity, we look at anywhere we've created a variable, because variables are the ones that consume memory. So that is where we check. So for example, here we have a variable here called total. So for the space complexity for this particular variable here is actually O of 1, because that variable is just one variable going to hold one value. On the other hand, we have another variable here, num. So again, we can say that here num is also giving us O of 1 time complexity. And we have another variable here, array. Arrays normally have a space complexity of O of n. So you've guessed it right. So if we add them and drop the non-dominant terms, you see the overall space complexity for this particular code will be O of n. So that is how we calculate the space complexity. We only look at the variables. So for normal variables, space complexity of 1. For arrays, space complexity of n. If you have a 2D array, for a 2D array, the space complexity will be O of n squared. If it's 3D, then it's going to be O of n cubed. So hope you remember that. Okay, so ladies and gentlemen, that is it. I hope you've been able to understand the different algorithm runtime notations, big O, big theta, and the other one was big what? So the worst case, the best case, and the average case. The big O notations, we have the linear time, the constant time. Those are the most common one, and also the algorithmic time, which are very nice. You've been able to add up the time complexities of code to understand the overall time complexity of the code and also space complexity. So thank you very much. This is not a very easy topic, and I'm also quite struggling with it. I encourage you to check up other materials, especially here on YouTube. And going forward, we are going to be writing code, and we're going to be analyzing their time and space complexities so that we can get better and better. So in the next video, we should look at arrays. So thank you very much, and see you in the next video. Bye.